Sorry, just one question. What's the main difference between dy or over dx or d over dy or d over dt?
Well, t is just another variable. And so dt, when you use dt, we are assuming that x is a function of t and y is also a function of t. So if that's the case, then we have it's different. I mean, the dy over dt is a change in y over change in x, and then we can take the limit, and dx over dt, which we are actually, it's a different quotient. It's a difference quotient. So the meaning is different. So when you write dy dx, what it means as x is changing, how is y changing? So that is commonly known as a slope. And then if you have anything else, like dy dz, or dA over dB, or dz over dy, or dz over dw, it's actually a limit of the ratios. So as one variable changing, how is the other guy changing? That's what it is.
Oh.
So mathematically, there's different meaning. It's a ratio of two, how the two variables are changing. How are the relatively, how is one variable changing when the other variable is changing? So the meaning is different. So when you get to the later examples that you'll see, when you get to the word problems, the word problems will have all those issues.
Do you have any
Okay, so right now it's both basically symbolic. It's kind of hard for me to give you meaning right now. But in the next section, when you do word related rates, when you get to word problems, it will be more interesting because we will not have meaning to all of these expressions here. So when you have DDT, this is referring to time. So many times we don't know how fast things are changing when time is changing. So in that case, we apply DDT. So even though there's DDT here, DDT is very, very common within math and all the sciences. And of course, if you take other courses like biology or astronomy or whatever science you take, the DDT is very common because we want to know how something is changing when time is changing. So we want to know how things are growing. Then basically we want to know what we normally call the speed is DDT. Because speed is something is changing by time. Okay? So when you get there, you will see it will have more meaning to it. Okay, so if you have no other questions here, then on example 3 or 4, I'm going to now save it and then clear all this. And now let's get to some problems here. So now let's get to the fun part. Let's look at example 5 and 6 and 7. I only have these 3 equations here, but you are always, you should always look for more problems. Again, class. Of you should have access to one of the textbook or online textbook or something, or from the internet. Look up problems. And for example, for implicit differentiation on the internet, all you have to do is type in implicit differentiation, and you will see a bunch of problems. Okay. So now example 5 and 6 and 7. Now, but the first example 5 is actually a slightly easy one because this is x squared minus plus y squared over 5. 25 is actually a circle. So let's see how things are. So first, even though the graph is not required, but why don't we graph this anyway? And let's try to understand what's going on, okay? So I'll try to graph this. So what is the graph here? So let me see. Yeah, the drawing is here. Yeah, that's easy. I can draw a circle right here. Oops, thick. It's too thick here. So what I'm going to do is I'm going to make it a little bit thin. So this is a circle, and the graph looks like this. And this is a circle, radius 5. Radius 5. This is radius 5, yeah, the radius 5, and the radius is 5 here, so I can just write a 5 here. And of course, the center of the circle is the origin right here. And now, find the tangent line to the curve x squared plus y equals 25 at the point 3 comma negative 4. So this is negative 5 here, and this one is 5. Where's the point 3 comma negative 4? Looks like the 3 comma negative 4 is going to be 3 comma negative 4 is going to be here somewhere. Here somewhere. That's the point 3 comma negative 4. It's something like that. So approximately the point 3 comma negative 4 is there. So let me just write this down. So this one is going to be 3, comma, negative 4. And you can see that if we draw a tangent line to the circle at that point, it is going to be positive, right? You can see that. Because the tangent line, yeah, we can kind of sketch it. Tangent line, maybe I draw this in brown. How about if I draw the tangent line? Maybe, let me see. How about if I sketch the tangent line like something of that sort, right? Maybe like this. Something like that. Yeah, there we go. So let me just put a question mark. This is just a sketch, of course. You can actually have a better estimate if your graph is more accurate. So again, in this case, I think 3, 4. Now the point 3, 4 is actually closer to this point right here. Again, this point 3, 4 is closer to the south pole over here than the point of the east. Okay, so that point is the east end, the 5, 0. So is the point 3, negative 4 closer to the point 5, 0, or is the point 3, negative 4 closer to the point 0, negative 5? Which one is it? Can you all see that the point 3, negative 4 is a point closer to the point 0, negative 5 than the point 5, 0? You see that? So it looks like it is going to be tilted a little bit less. So it looks like, by looking at the picture here, looks like the slope is going to be a little bit less than 1. A little bit less than 1, not more than 1, but less than 1. So less than 1, something. So I don't know, maybe 0.8 or 0.9 or something, 0.7. We don't know exactly, but that's my estimate. So you can have a better estimate, the better your graph is. Okay, so now this one here, I'm going to do this in 2 ways. This one by regular differentiation first, and then second, I'm going to do this by the implicit differentiation. Okay, how about this? Solution, or how about this? How about solution by, okay, let me do the implicit differentiation first. By implicit differentiation. So let's see how it goes. So if you want to find the tangent line by implicit differentiation, what do you do? Now we need for slope. Wait, what color am I using here? Is this brown? I guess I'm using brown. Okay, for slope, we must find what? Find what? What do we do? For slope, what do we have to find here? We have to find dy dx. We have to find dy dx. If dy dx is kind of the slope. The slope is defined as the change in y over change in x. So it's not dx dy, it's not dx dt, it's dy dx. So we have to find the slope, and the slope is basically dy over dx. Note that we have a dx in there. We have this dx in the denominator. So what we do is apply ddx to both sides. Apply what? ddx to both sides. Apply what? ddx to both sides. So ddx, d over dx. You have to apply dx to both sides. Okay, so if you do that, this is what we get. What we do get is this. ddx of x squared plus y squared as you apply to the left-hand side. And then now, we also apply dx to the right-hand side, which is ddx of 25. Oh, by the way, before we start the problem, one thing I ask you to do all the time, whenever you have a tangent line problem here and they give you a point, the very first thing is always what? Check if this point is on the curve. On the last quiz, some of you did not check. So when I tell you now, usually when I say a curve at something, and if I use the word at, then that means the point is actually on the curve. Or otherwise, I will say find the tangent line to the curve, which passes through, and then I call that, and then a point. When I say passes through something, then the first thing is you have to verify. There's no formula here. Check, check, check. Start here. You must check. Check, check, check. Is that clear? So whenever you get a tangent line problem and there's a point given, the first thing you should do is you must check. Now in this case you check it. 3 squared plus -4 quantity squared, that would be 9 plus 16 is 25. Yeah, it is on the curve. And you don't have to even write it down, but make sure that you check. A point may or may not be on the curve, especially when it says passes through something. That point may not be on the curve. Okay, so check. So don't tell me that you didn't know that. That will be a big penalty. So if you think that that's the point on the curve when it's not, then you blow up the entire problem. You're doing a much easier problem, so there is nothing I can give you at that point. All right? And that already happened on the quiz last time. Okay? I asked you to pass. Okay, so make sure that you know. Okay, you have to verify whether the point is on the curve or not, because it changes the problem drastically. So in this case, the 3 comma negative y, yeah, it is 3 comma negative 4. It is a point on the curve, so check. It is a point on the curve. Now we have this, and now what is this? Now it's time to take the derivative. Now this is now the derivative of a sum. This is sum, not a product. So we just have to take the derivative separately. The derivative of x squared with respect to x, that will be 2x. And now what is then the plus? Now what is now the derivative of y squared with respect to x? You take the derivative of that with respect to y, so that will be 2y. And then we now have dy dx. This is 2x plus 2y dy times dy dx, and then that is equal to, what is the derivative of 25 with respect to x? And that will be 0. A 25 is actually a constant function, therefore we get 0 here. So now from here, what do we get? We now get this. We now get dy dx, solve for dy dx, and then if we do that, then what do we get? We multiply both of a half, and 2's will go away. And so now, dy dx is equal to now minus x, and then over y. That's what you get. Any questions so far? So we get dy over dx is equal to now negative x over y. Now, how do we actually find the point? How do we find the slope at that point? So now, what do? We must find the dy dx at that point 3 comma negative 4. So how do you do this? We are going to do this. We have to evaluate this dy dx. What is the value of dy dx at 3 comma negative 4? Now note that in this case, this guy not only has an x, it also has a y. So in this case, I'm going to put a vertical line here and evaluate this at 3 comma negative 4. So this is what we are going to say. To evaluate dy dx at the point 3 comma negative 4. Note that this dy dx has an x and a y in it. We both have x and a y. So we cannot just plug in x equals 3 as we did previously. That's what we do when we take the derivative of a function, then we just plug in the x value. But for implicit, now we have to plug x and y. If you have y, sometimes you only have x, and sometimes you only have a y. That happens too. But in this case, therefore, what is that? That will be minus, and now we plug in the values. What is x? X is 3. Now, what is y? Y is now negative 4. So we get this. Make sure you plug in correctly. And when you do that, what is that? Now we get the slope. This is now equal to 3 over 4. So this here, right here, slope is 3 over 4, and that is the slope of the tangent line. So therefore, what is the tangent line? Tangent line, therefore, is equal to, it passes 0.3 comma negative 4. So now we can write the equation y plus 4, and y, okay, is equal to, that is y minus negative 4, and the slope is now 3 over 4, and then times x minus the point x minus x1, or a, that will be 3 in this case. So this is a line whose with slope 3 over 4, and comma negative 4. This is now the tangent line equation. Actually, I can also give it the normal line equation. Normal line equation will be this line. The normal line. It's a tangent line. The normal line equation, now this is not a vertical line or a horizontal line. When it's not a vertical line or a horizontal line, then you can what? You can apply the negative reciprocal property. So therefore, in this case, that will be x plus 4. And then what is the negative reciprocal? And that will be minus 4 over 3. And then times, what? Times x minus 3. Once again, when a tangent line is horizontal or vertical, then you cannot apply this theorem. The product of two slopes negative 1. You can only apply this for slopes which are not 0 and not undefined. Okay? But if the slope is 0, or if when you're dealing with a horizontal line or a vertical line, then you cannot apply that rule anymore. So in this case, this is what? This is 3 over 4. Yeah, we get 3 over 4 here. So that is the answer, and yeah, that's it. How about this? Let me now erase this example 6 here. How about if we do this in a different way? Let's do this. How about this? This one? Let's do this now in a different way. The second solution. This is second solution. Solution 2. This is by regular differentiation. The differentiation we have learned so far up to the last section. What is it? Okay, let's do this. Now in this case, if you want to do this by regular differentiation, then the first problem is we have to solve the y in terms of x. So the question is this. So now what we get? Y squared is equal to 25 minus x squared. 25 minus x squared. You get this. And then from here, you get y is equal to plus or minus, and then square root of 25 minus x squared. You get this. The first hurdle you have to pass is this. When you solve for x, when you solve for y in terms of x, you get this plus minus here. The question is, which one do we choose? And if you don't choose the correct one, then you will actually make a mistake here. So in this case, do you think we should choose a plus? Do you think we should choose the plus, or do you think we should choose the minus? What do you think we should choose? Which one do we choose here? Which one do we choose to take the derivative for this problem? So do you think we should choose the top one or the bottom one? If you have no idea, so you just pick the positive one because we don't know. So if you don't know, you just pick the positive one, right? In fact, that's what many students do. Many students don't know what this plus or minus is doing. So you know what they do? They just put the plus. They just choose the plus sign. Well, you know, in this class, I will never make the students lucky. If you just choose one, then that could be wrong. So just say which one do you know you have to choose? Well, if you look at the top half circle here, so let me write this in color. How about this? Let me use green here. If you choose the top half circle, you know what? How about this? Let me use a slightly thicker marker. If you choose a top half circle, what is the equation of the top half circle? This top half circle is actually what? Y is equal to square root of 25 minus x squared. So this guy is actually y is equal to 25 minus x squared. And as you can see, y is positive. It's this guy right here. Now, this bottom half right here, what is this bottom half? This bottom half here is actually, you know what, maybe I'll change the color here. How about if I use maybe blue? So let me choose blue here. Blue is this bottom here. If I choose the blue here, the blue here is now what? Y is equal to minus square root of 25 minus x squared. So this is y plus 25 or minus x squared. Minus and then x squared. So the top half circle is y plus square root of 25 minus x squared. The bottom half circle is y is equal to minus square root of 25 minus x squared. And now in our case, do we choose the positive one or the negative one? Which function now? These two half circles, they are actually functions. Because for each x, they only have one y. And the boundary point, 0 is at 0 and negative 5. Those points are included in both. This point right here, they actually include in both top half circle and the bottom half circle. So they belong to both. Now, note that the question point, 3, negative 4. This point right here, that's where the question is on our problem. So now, what is that? Oh, now it's this guy right here. So we now have to pick positive one. So what do we choose? Choose the negative. So y is equal to what? Y is equal to minus square root of 25 minus x squared. Now, does everybody understand why I chose the negative one? Why? Why did I choose this function? This is not a function, by the way. Y is in terms of x, so that is a function. So why did I choose the negative one? Because this part of the function, so let me write, oops, this part of the function, this part, this part contains a point, what? 3, negative 4. So you have to look at the given point. So the point we have, the point in question is 3, negative 4. So we are interested in the curve near this point. So near that point 3, negative 4, well, that is the bottom part. And so that's why you have to put the negative there. So many students don't know what to choose here, and they just choose a positive one, and then now we'll get wrong once you do that, of course. So now from here, now we can take the regular derivative. What is that? That is equal to now. So what is now dy dx? So dy dx is now the regular derivative, and now we have to apply chain rule. This is going to be the negative factor. We just take it out. Now what is the derivative of square root of x? The square root of x, the derivative is now 2 times square root of that, which is 25 minus x squared, and then minus x squared. And now take the derivative of that with respect to 25 minus x squared, which is minus 2x. So what we end up getting is this. This is equal to x over, and then square root of 25 minus x squared. Get this right here. Oops, you get this. So 25 minus x squared. Now what is the slope? So now what is the slope here? The slope of tangent line is now going to be this. Slope of tangent line, this is now the slope of the tangent line. The slope is going to be what? The slope is going to be the dy dx. So once again, let me just continue writing. So that would be dy dx. dy dx. You included at the point 3, negative 4. Actually, in this case, we don't need the y. So if you just want to write x equals 3, and that's fine, because in this case, there is no y. So what is this equal to? This will now equal to 3, and then square root of, go to what? 25, and then minus 3 squared. When you plug that in, what do you get? We get 3 over 4. Square root of 25 minus 9, which is square root of 16, which is 4. So we end up getting 3 over 4. And so we end up getting 3 over 4. So now you take your pick. Do you like the regular derivative, or do you like the implicit differentiation? Do you like the regular differentiation, or do you like the implicit differentiation? Just compare. What do you like better? Am I going to accept either one? Yeah, I will accept either one. Sure. If you do regular differentiation and get the right answer, I'm not going to, say any comments, so that's okay. Although that's not the best way, you can do it. But the problem is, on example 5, you can do it by regular differentiation, whereas example 6 and 7, the regular differentiation is not even possible. The reason why regular differentiation is even possible here on example 5 is because we can separate the x, we can solve for y in terms of x. even though there's a plus minus there, and that's a slight complication there. But because this is not a function, you will have this plus minus going on somewhere. Okay? Because this is not the circle is not a function. And so at least though, in pieces, we can convert that into a bunch of functions. In this case, two functions. Sometimes you might need more than two functions when the curve is really messy. Okay? But in this case, you can do that. But even then, as you can see, the calculation for regular differentiation is actually more messy, as you can see. There's probably more chance to make the mistake. And then once you get the slope, then of course you can get the write the tangent line by using the slope and the point, and then you can get the normal line. The normal line was by the not part of the question, but I just wrote it anyway, okay? Because on other problems, I might ask you to get the normal line. By the way, for a circle, there's a very simple formula. The simple formula is that the normal line is always the line. For a circle, on circles, the normal line is what? The normal line is always a line connecting the center to the point to the tangent point. And if you connect the what? If you connect the center, and the tangent point, then that is the normal line at that tangent point. So the normal line at that tangent point is the same line as the line connecting the center of the circle to the tangent point. So that is the case for circles only, not for other curves. For circles, okay? Circles, you can get the normal line. This is almost like a formula, okay? But this is only for circles. Generally, that is not the case. Of course, a regular graph doesn't have a center. So, okay? All right, any questions here? Any questions on example 5 or 6? So you didn't do that, sorry, not 6. Example 5. This is only example 5. Any questions here? Okay, let me save this, and now let me clear this. Now let's move on to example 6. What is example, example 6 and example 7? Let me just do example 7, okay? Example 6. Okay, now, you know what? I don't think I'm going to do example 7. Maybe I'll let you do example 7. Well, should I do example 7 or should I do example 6? Which one would you like to see? I'll just do one of them.
Could you do 7?
Okay, then I'll let you do example 6 on your own, okay? All right, is that fair? Do example 6 on your own. Again, very similar. There's nothing much new here, okay? So let's look at it. Then how about now example 7? So first of all, 2, 0. Is this point on the curve? Let's see. If you plug in this 0, 2 into this equation here, what do you get? We will get that y equals 0, we get 0 on this side. So if you plug in the point 2, 0 here, you know what? 1 second. Let me just clear this. Let me create some more space. Let me just pull this over a little bit more. Okay, there you go. A little bit more space now. So in this case now, first, let's plug in the point 2, 0. And if you plug the 2, 0 onto this equation, that means x equals 2, y equals 0. So y equals 0, the 2 times 0 is 0. And then 0, and then 2x equals what? 2. So x cubed is 8. And then plus, and then note that x equals 2, so y equals sine y is 0. So this guy actually becomes 0. Because sine 0 is 0. So x times 8 times, so should I just write, okay, 8 times sine 0 is 0, and then minus 8. Okay, there you go, check mark. So it looks like that 2, 0 is actually a point on the curve. Check this? So that's a check mark. You know what? That is a check mark. So check mark is what? Right there. Check. Oops. Too close. So check here. Okay. So that point 2, 0 is a point on the curve. I just verified it right here. Again, whenever you're given a point, do not assume anything. All right. Always verify. Whether they tell you that it's point of the curve or not, you have to just check the point, check the given point. It is always a must. This should be part of your habit. Check if the point is on the curve. Check it. Now, although usually when they say ask, assume that that is a point of the curve. Okay? But sometimes you have to be very careful. Sometimes the curve may look like this. And then when you look at it, and then you will have 3 points right here, and then 3 points, they all have the same x value. And then the given point might be one of the points here. Now, when you have a point like this, note that these other points may you know what, they also have the same x value. So it could be like this. So that's the x and the y. And so I just want to remind you that a curve, a curve, which is not a function, and this one is has a y here. You know what? This does not seem like a function. You can try this on the graphing utility and graphing calculator, but I don't think this will be a function, okay, from x to y. It has a sine y and a y in there, so we don't know exactly what's going on. But my feeling is that this is probably not a function from x to y. So what I'm saying is you may have different points with the same x value. So later on, when you actually solve the problem and you try to find the point on here, instead of finding this tangent line, you might end up getting this tangent line. So let me do this here. Be careful. The tangent line you have to find is this, let's say, and then you might end up getting this line, or maybe this line right here. Because they all have the same x value. Watch out. Anything goes here. So be very, very careful. All right, is that clear? Be very careful here. Weird things could happen on all of these curves here. So again, I want you to first check whether the point is on the curve. So now, what we want to do is, okay, now, since we want to find the tangent line, we want to find the slope. And the slope is defined as dy over dx. So this is how slope is defined. So that's why we want to find dy dx. And if you want to find dy dx, then we need to have a dx in the denominator. So what we want to do is apply ddx to both sides. So what we'll do is this. So the first is, okay, to find slope, what you do? To find slope, that is the slope of tangent line, what do you do? We do this. Apply the ddx to both sides. ddx to this, which is what? 2y. And then ddx apply to, and then ddx on the right side. So we have the equation, copy the equation, and then apply ddx to both sides. That is, we will take the derivative of both sides with respect to x. It's not x cubed, and then plus x sine y, and then what? Minus 8. And by the way, cannot solve for y in terms of x. In this case, even if you want to apply regular differentiation, you can, because we cannot solve for y in terms of x, because in this case there's a y here, but note that there's also y here. How in the world are you going to combine this y and that y? There's no way to do it. So algebraically, there's no way to do it. For those of you who get into Calculus 2 next semester, you are going to study what we call Taylor series. And then when you get there, power series, when you get there, there's a way to somehow combine those y's there, but you know what? In this case, even that method may or may not work. In this case, it's virtually impossible. Okay? So in this case, you cannot solve for y in terms of x. So the regular differentiation, even if you want to, is not possible here, because we cannot solve for y in terms of x. Just like the example 6, we could, even though we get two parts. Okay, so in this case, the only way is to find the derivative by implicit differentiation. So we take the derivative both sides with respect to x, and if you do that, this will now become 2 times, and then dy dx. The constant multiple formula for the derivatives, you can pull out the 2, and so we get 2 dy, and now is equal to, now what is the derivative of the right side with respect to x? This is what this right here. The derivative x cubed with respect to, and note that this is all plus here, so we can take the derivative separately. So this is equal to now 3 x squared. Okay. The plus, now we have x sine y. You have to take the derivative with respect to x. So now we have to apply product rule, because x times sine y. So this is f prime g. The f prime g will be sine y. f prime g plus fg prime fx. Now we have to take the derivative of sine y with respect to x. So take the derivative of sine y with respect to y, which is cosine y. And then now, the chain rule factor, we must have that dy over dx. Chain rule factor dy dx must be there. This is times. And then minus the derivative of 8, which is 0. So that's gone. Now, what we want to do is we want to solve for dy dx. Plus all the dy dx to one term. Bring that all to the left-hand side. And then what? And then what? Divide both sides by the coefficient. So now I'm going to skip one step here because it's too much to write. So what I'm going to write is 2y dx is equal to, what is equal to 2 minus this, so that will be 3x squared, and then what? 3x squared plus sine y, and then what? Divide by, both by 2 minus x cosine y. So there you go, that's dy dx. Okay? Class, any questions here? Any questions up to this point? This is the hard part, up to now. Any questions here?
No.
Now, what is the next step? The next step, you now have to find the slope. So to find the slope, what do? We now have to, what we have to do is now we have to find the slope to the tangent line at that point. So now dy dx, now what do? Dy dx, now evaluate this at the point 2, 0. That means x equals 2, y equals 0, plug that in. If you do that, then what do you get? And now that means x equals 2, y equals 0, x equals 2, y equals 0. So now the denominator we get 2. And note that y equals 0, so we get cosine 0 is 1. You know what? This is not the best point. Well, I guess I did not, you know what? This is, the problem itself is not wrong, but this is just a difficult case. Okay, so here, let me do this here. Yeah, you know what? This is not the easiest case here. It's not wrong, but it is. This is not the easiest case. So now let me explain to you. When you plug in x equals to y equals 0 here, we actually get minus, and then 2, and cosine 0 is actually 1. So we actually get 2 minus 2. And then when you look at the top here, what do we get? 2, plugging 2 there, we get 2 squares there, we get 12. And then minus, and then plus, and then we get what? We get 0. And so we end up getting 12 over 0. And then you might say, what is this guy? Oh, it's undefined. Undefined. Yeah, undefined. But you know what? Let me tell you this. But this curve is a smooth curve. That means as a tangent line at every point. How do I know that this is a smooth curve? Because when you look at all these expressions right here, what we see this guy, 2y, that's a smooth curve. Y is changing very nicely, and then x cubed, that's a polynomial. And then 2y is also a polynomial. And then plus x is a polynomial, and sine y, it's not a polynomial, but it's actually a smooth curve. So the values don't change suddenly, and it does not have an absolute value, things like that. So there's no sudden change. When y changes little, then sine y changes little. When y changes little, then what 2y changes little. When x changes a little bit, then x cubed also changes a little bit. And then minus 8 is constant. So therefore, by looking at this function here, everything changes slowly. So whether it be y, 2y, x cubed sine y, or x times sine y, all of them, when x changes a little bit, y changes a little bit, there's no point. by this. So now this is something you will not know, but in this case, that's what it is. So in this case, undefined, you know what? That means at this point, what happens here? We actually have a vertical line. Oh. Question is, may not have a tangent, may not have a tangent line, may not have a tangent, or what? Or, let me write it down, or may have a vertical tangent line. May have vertical tangent line. So in this case, actually, because this guy is actually a smooth function, we actually have a vertical tangent line in this case. Okay? So now this requires a little bit more information here, but the 0 here, undefined, vertical. In this case, what is the tangent line going to be? The tangent line has to at what? At what? What is the point here? At 2, 0. So what is the tangent line? At 2, 0. Where is it gone? At 2, 0. Tangent line is what? Is going to be what? X equals 2. This guy. You know what? On the test, I'll probably, you know what? I think we will be ready to take care of these vertical tangent lines when we get to chapter 3. Officially, the vertical tangent line is not covered in chapter 2, but it will be covered on chapter 3. Is that clear? On midterm 2 tomorrow, there will be no vertical tangent line. But on midterm 3, which will cover chapter 3, there will be vertical tangent line. Okay, so let me just say that. Because when you get to chapter 3, we will be learning about curve sketching, and we will be dealing with vertical tangent lines here. Okay, so right now, so if you know what, should I try to type it in and see how the curve actually looks like? Okay, so let me now curve this here, and so x equals 2, that's a tangent line. Yeah, I have to write x colon, and I forgot to put a colon there. That's colon, and it's actually x equals 2. How about this? So let me save this, and then I'm going to clear this. So now what I would like to do is let's go to the website here, and let's see how this curve actually looks like, and then we'll see what's going on, okay? So decimals here, yeah, decimals. This one here, let me erase all that. Yes, this one here, okay, let me just, number 14. What is the equation? The equation is 2y. 2y is equal to what? Is equal to x cubed. X cubed, let's see, what is x cubed? X cubed, okay, x cubed, and then what? Plus x times sine of y in the minus 8. This is how the curve looks like. There we go. Oh, curve doesn't look that bad. But you know what? Does it look like a function to you? It kind of looks like a function. It's not clear whether that is a function or not. But when you look at this here, there we go. So you know what happens at x equals 2? Looks like we do get a vertical tangent line right there. So if we magnify this part, let's see what happens. Yeah, indeed. Yeah, that's right. Look at this. We magnify this part right here, x equals. When you magnify this infinite times, what happens? So this guy right here, it kind of looks like it's x equals 2, right? So the linear behavior of the curve near that point, that is what we call the tangent line. In this case, the tangent line is actually x equals 2. Okay? So now, do you think this is really approximately the line x equals 2? I think this is approximate. So if we magnify this more and more, I don't think this will be a line. But this is so flat here. Again, if we magnify in infinite times, are we really going to get vertical here? You know what? I think we have to increase this to maybe 1 trillion or something. Otherwise, we will not be able to see what's going on here. Okay, so now, but anyway, I think this is good enough for now. So in any case, at x equals 2, we actually do get a vertical tangent. Again, vertical tangent will be covered on midterm 3. That is on chapter 3. Okay, so on this test, on tomorrow's test, there will be no vertical line, vertical tangent line. All right, except for horizontal tangent, it is covered. So when you get a horizontal tangent, you get a vertical normal line. And vertical normal line is covered on the test, but vertical tangent line will not be covered. Not on midterm 2, but it will be covered on chapter 3 and midterm 3. All right? Any questions here? So let me take a break. The time is now what? 9:54. Let's take a 10-minute break. We'll meet at 10:04. Class, 10:04. We'll have a break. So let me just write down 10:04. What is the So we have 10-minute break. Continue at 10:04. Okay, I'll be back in 10 minutes, and then we'll start the next section. because I'm back here now, let me see. Let me write some equations here. We have absolute value here.
Professor, are we starting chapter 3 on Wednesday?
We'll start chapter 3. So we'll start chapter 3 tomorrow.
Okay.
Or Tuesday. Tomorrow we'll have full lecture. We'll have full lecture, and then I'll start chapter 3. And of course, I can spend a little bit of time answering your questions, but we will start chapter 3. Yes. And then the test on chapter 3 will most likely be early next week sometime. But we don't have that much time here, so we'll see. Okay. So we have this. Okay. So let me see. How about 1 second here? Let me show you some graphs here. 2/3, 2/3. Okay. Okay, class. Let me now show you some graphs here. I'm going to show you some graphs, and the graphs are like this. And sometimes, even I don't know, how smooth the curves will be. But when you look at like number 13, I showed you is actually a smooth curve, relatively smooth. Okay, it's not. I mean, it is like going, it's kind of the turning, right turn, left turn, and so on. But more or less, there's no sharp turns, basically, no sharp turns. And that's because when you first of all look at this equation, number 13 in red, 2y plus x2 plus xy, x times y sine y minus 8. First of all, there's no denominator. and there's no like square roots or things like 2/3 powers like this, and therefore everything is kind of smooth. So in this case, every function you see is kind of smooth. What that means is when x is changing by little, y is changing by little, and it is not making a sharp corner. So we know. So in this case, we know that we will have a vertical line, we will have a tangent line at every point. And sometimes that happens to be a vertical tangent line. Now let's look at examples such as example 12. This is x to 2/3 power plus y to 2/3 power equals 10. And when you look at the graph here, now we see these corners here. And that's because we have these 2/3 power. When you have a 2/3 power or 4/3 power, then this is like the indicator where you might have something which has a sharp turn. So let me just erase this first, annotate, and then clear all this. Okay, so these are sharp turns. So when you have 2/3 power, which is the same thing as cube root of x squared. So these are the indicators. When you have things like this, then we might have a sharp turn, and that's what we see right here. Now, that's that. Now, how about if you look at our example 12, example 11? Example 11, we have x to 2/3 power 2, but you know what the graph looks like this, and it doesn't really have any sharp turn here. But things are undefined here, over here. So again, you know what? By looking at there's so many graphs out there, so many equations out there, it's hard to figure out what's the what. But let's say, how about if you now look at let's say example number 10. Number 10 equation. This is absolute value of x plus 2 times absolute value equals 12. Absolute value is generally a source of having a corner like this. So it's like this, and as you can see, it's a diamond. So when you have absolute value, let's say absolute value, and then let's say absolute value, and then doesn't matter. How about if I put like x, y here? How about let's say x, and then what plus y, and then y, and then what minus let's say 3. Well, what do we get? Well, let's see. Do we do it a curve here? Where's the curve? Oh, I don't see any curve here. Where's our curve? Something, a mistake here? Let me see. Number 10. Clicked it. You know what? I'm not sure why. Oh, maybe it's because is it an empty set? Could this be an empty set? I guess it could. Yeah. You know what? I see. You know what? I actually typed in this equation number 10, and then when I actually look at the graph here, I don't see anything. What do you think is the reason? Now I know. Now I see what the reason is. You know what the reason is? It's an empty set. That's why. If I change that to plus 3, well, something will show up. What is that? Plus 3? Is that plus 3? What is the graph here? Kind of looks weird. I see. How about if I make it, let's say, plus 4? Plus 5? Okay. What is this? Plus 7? Oh, kind of weird. What is this? Well, that's kind of weird. How about if I, let's say, make it like this, and then maybe copy this. Let me copy this here. Copy. And then let me copy it over here, number 12. And how about if I make it, let's say, 2 here? Then let's say this. What is that? How about if I make it minus here? How about 5 here? Okay, so anyway, let me erase this. Clear this. So what I'm trying to get at is, sometimes I don't even know how these graphs look like, but let's say, how about this? Instead of this, maybe I'll change it to 3. 1 second here. Let me do this. How about if I plug in a 4? It kind of looks like this. Like this. Oh, there's only one corner. One corner there. How about if I make it, let's say, plus the absolute value of x minus y. Let me see what we have here. So absolute value of x, and then plus, so let's say, how about 2y, and then absolute value. Let's see how this is. Will this give us some graph? Oh, there's a little kink there. How about can I somehow magnify that part right there? Let's see, what is this? Oh, there's a little weird, like a kink. You know what? Anyway, so how about if I make this into the 3? Oh, it turns. If I make it 4, it turns like this. How about if I make it 9? Oh, it goes like this. So anyway, how about let's say 2? Oh, there we go. Anyway, what I'm saying is, when you look at these equations here, whether you have a denominator or like a square root or maybe 2/3 power or absolute value, you know what? Other than these unusual functions, if you only see like polynomials and sine and cosine and exponentials and logs and even trig, and you don't have a denominator, then usually what happens is they are very smooth functions. That means if it's smooth, that means there's a tangent line at every point. And by the way, I didn't show you the circle here. So you know what? Now let me erase this here. How about the circle? You know the circle here? X squared plus y squared is 0. Is equals 25. X squared. Where's my circle? Oh no, not that. Sorry. X squared. And then what? Plus y squared is equal to 25. So as you can see, it's a circle here. Now, a circle is also a smooth function. So what do you think would happen at the point 5, 0? So you know what? This is a circle 5, 0. What happens at the point 5, 0? Do we have a tangent line here? Class? Do you think the circle, the x squared plus 5, y squared plus 25, that circle equation, does this circle have a tangent line at 5, 0, which is the east end, the right end point? The right end point, do we have a tangent line? Yes or no?
Yes.
Yeah, we do. It happens here with the tangent line. So now, when you apply, you know what? This is dy dx. Let's see, what is the dy dx for the circle? The dy dx is actually what you get 2x dy dx.